Alright, AP Chemistry, this is a continuation of the answers for day 74. These are the book problems. Again, these are the only ones you do, are the ones that I've actually copied into the assignment, not that entire list that's at the beginning of the assignment. That's just for my reference, so I hope that didn't confuse you. So let's go ahead and continue on with 9.2. So if the three balloons shown on the right are all the same size, what angle is formed between the red one and the green one? Well, you're going to have to, since this is, I couldn't copy this in color, let's just say this is the red one and this is green, and I don't know what other color they have here, but we'll just leave that as red and green right there. Okay, so it's if you look at those balloons, they're going to form a flat triangle. Okay, so that would be trigonal planar. It would look like that. So that's going to be a 120-degree angle. Balloons are actually a very good representation of these molecular geometries. Unfortunately, again, we're not in the classroom where we can actually do something hands-on like this. Okay, so you can go ahead and just write 120 right there. All the other angles are 120 as well. 120, 120. Okay, so A is, you can just write the number. You don't have to write a complete sentence here. If additional air is added to the blue balloon, okay, so I guess this one's blue, so that it gets larger, what happens to the angle between the red and green? So if you expand this, what this is simulating is a lone pair. Lone pairs are effectively like expanded electrons over here. Why is that? Because they don't have any nucleus of an atom, protons, to offset the negative charge. So it's just pure negative charge here. So that's going to push this balloon this way. Actually, it's going to push this balloon this way and this balloon this way. So it's going to decrease the angle. You don't know how much or what the number is, but it's going to be, you can just say less than 120-degree angle. Between, you got to be specific between red and green, because between blue and green or blue and red, it's going to get bigger. The angle's going to get bigger. Okay, what aspect of VSEPR model is illustrated by B? And we just said that. That's a lone pair. That would be this. Lone pair, and these two get pushed to be less than 120 degrees. So that would be an AX2E1 configuration. So that would be lone pair. Okay, and that's that for 9.2. Okay, so just be sure you understand those concepts and why that is. Okay, shown below, 9.6, shown below are three pairs of hybrid orbitals with each set at a characteristic angle. For each pair, determine the type or types of hybridization that would lead to hybrid orbitals at the specified angles. Alright, so the first one is 90 degrees. So you go over to your sheet. The only one where you find 90 degrees, well, let's just say, where do you find 90-degree angles? Okay, so you could find them here. So it could be, with the hybridization, would be SP3D, because they're only showing two of the balloons. You don't know how many others there are. Or the other possible one is down here. These are all 90 degrees, and that's SP3D2. So you can say either one of those. So you can say D2. Those are the only two where you would find any 90-degree angles as well. Okay. Okay, 109.5, that's one that you should almost have memorized. That's a tetrahedral. Okay, you will see that a lot. So that's tetra. And finally, 120 is what we just talked about. This one up here is trigonal planar. And that would be, and I wrote tetra, I should have written SP3. And this one, I'll write the name, but they asked for the hybridization. Trigonal planar. Right here. and that's sp2. And that's all you need to do for these questions, all right? You don't need a long explanation as long as you understand it. Okay, 9.5. The plot below shows the potential energy for two chlorine atoms as a function of the distance between them. A. To what does an energy of 0 correspond in this diagram? B. According to the valence bond model, why does the energy decrease as Cl atoms move from a large separation to a smaller one? C. What is the significance of the clcl distance at the minimum point in the plot? D. Why does the energy rise at clcl distances less than that of the minimum point in the plot? And E. How can you estimate the bond strength of the clcl bond from the plot? Okay. Okay, so let's look at what's happening here. This is the distance. And as you go to the right, the distance is farther away between the two atoms. It means the distance between the two chlorines. And this is how much energy. So if you look at this here, this is when the chlorine and the chlorine are far apart. They don't feel each other. They don't feel any attraction. They don't feel any repulsion. So relative to each other, they're at a 0 energy level. Okay, as they get closer together, chlorine forms a diatomic molecule. It likes to form Cl2 in its natural state. So as they get closer together, they're attracted. Remember what we said, chemical bonds happen when the elements involved can lower their energy. Things always want to go to lower energy. All right, so this represents the distance where they are bonded. They're happiest because they're at their lowest energy. So as they get closer to each other, right here, they're going to lower energy, so they're happy. They like that. They want to be going to lower energy. As they get here, this is the bonding distance. When they finally bond, this is the distance they're going to want to be apart because it is the minimum energy. And they want to be at the minimum energy. They want to be at the lowest energy state they can be. Now, this represents if you push them, start pushing them, forcing them to be closer together than they want to be, then they're going to start repelling each other. All those electrons being squeezed together and protons being squeezed too close together, they're going to repel. It's going to be like pushing on a spring. And so that energy, this potential energy, is going upward. And it's getting to where it's going to be a positive potential energy, meaning they want to spring apart. They want to push apart. They'd like to get back to this distance. So again, just think of it like a spring. So this is pushing them together. Pushing them together closer than they want to be, and that's why this would be going up. Okay, so this is represented by this, and this is represented by this. We'll just say that there they are, they're covalently bonded, and that's their bonding distance. And this would be represented, I guess I'll put it up here, by this. They're too close together. They're too crowded together. And so they're going to want to push backwards to this, okay? So let's read these questions. To what does an energy of 0 correspond? That's this one, okay? That's E. This is E. Energy equals 0. It means they're far apart. I want you to put this in your own words. You can draw this diagram, and I still want you to put it in your own words and write a complete sentence on this. Okay, according to the valence bond model, why does the energy decrease as Cl atoms move from large separation to smaller one? Because they are attracting each other, and they're going to the lowest energy state. That interaction between the protons in each atom and the electrons in each atom is just right. They're sharing electrons. This is where they have an octet and a covalent bond. This is really their happy place right there, okay? Octet rule, covalent bond, all that stuff that we talked about, that's where that happens right there. What is the significance of the clcl distance at a minimum point in the plot? And that's what we said, it's the lowest energy. I'll go ahead and write that. You go ahead and put this in complete sentences. Lowest energy. D, why does the energy rise at clcl distances less than the minimum point of the plot? And that's what I said here. Pushing them closer together, you're crowding the protons and electrons too close together, closer than they'd like to be, so it looks like that. And so they want to push apart. Okay, that's why the energy starts to rise as the distance gets less and less. And finally, how can you estimate the bond strength of the clcl bond? It's by the bond length. Shorter bond length is stronger bond strength. Now, you don't have specific numbers here, so bond length, you can just say bond length is related to bond strength. But you don't have specific numbers, so you can't actually come up with a number. Okay, and that's that. That's the answer. But I want you to write this out so you maybe save yourself some space. Just write complete one sentence for each of those is enough, okay? All right. Or you can write a paragraph and include them all in one paragraph. That would be fine too. Okay, 912. Methane CH4 and perchlorate ion are both described as tetrahedral. What does this indicate about the bond angles? All right, so again, just come back to your chart, and they both have 4 bonded atoms. You can see there, H4 and O4. Don't worry about the ion part of it. So it's 109.5. Okay, so A, again, I'm just writing quick answers. On this one, it's okay to just write the number, just get through it. It's fine. What does this indicate about the bond angles? The NH3 molecule is trigonopyramidal, while BF3 is trigonoplanar. Which of these molecules is flat? Well, the trigonoplanar is, right? That's a flat molecule. This one isn't. It's a triangle, but it has a lone pair. That pushes these arms down. All of these arms get pushed down. So it forms like, if you can kind of imagine what my fingers are forming, like a pyramid. My fingers are forming a pyramid where up here would be the boron, and the 3 fluorines would be down here, and they'd be pushed down like a pyramid. Okay, 3-sided pyramid. All right. So the answer to B is trig plane. Okay. Give the electron domain and molecular geometries for the following molecules. Okay, so this is what we did on all of those problems that I gave you on this assignment before we got to these. So we're going to do a few more. Okay, so HCN. So you may want to do this on another piece of paper. There's space here, maybe enough. So HCN is going to look like this. You got hydrogen, carbon, nitrogen, and there's 1 of each. So this one's got 1 valence electron, this one's got 4, and this one's got 5. That's a total of 10. And when you draw that, we drew this back when we were doing covalent bonds. It's going to look like H, C, N. We have to use up 10. And I'm kind of speeding through the construction here, but remember the rules. We first single bonded and then we place the other. So we have 10 electrons, everybody has an octet, and that's it. So that's it. So this has 2 bonding domains. So we have electron domain and bonding. And just write the AX notation for carbon. So it's A. It has 2 bonding domains, 2 electron domains, and both of them are bonding. So it's AX2E0. There's no lone pairs. So both of them are going to be linear. Okay, so right here, AX2E0, linear and linear. When there's no lone pairs, that means the bonding domain and the electron domain are going to be the same. Okay, let's do SO3 2 minus. That means it's going to have 2 extra electrons. So we have sulfur here. Just write what we're doing first. Okay, there's 1 of those times 6. and then 2 more that are E minuses. So that brings it up to 26. Okay. All right. Again, that's the 2 ions here. So we're doing B here, A here. All right, so let's draw that. So that's simply going to be S. And then we're going to place the O's. Again, don't put them at angles when you're doing this part of it. I wouldn't. You can if you want. So there, those are bonded. We need to deal with 26. Again, do this with pencil. I've been writing with pen. Do it with pencil because you're going to have to erase electrons when you do this and place them in different places. Okay, there's 8, 8, 8, that's 24, and 2 more up here makes 26. Okay, so everybody has an octet on that. All right, so for sulfur, you're only interested when it comes to geometry in the central atom, because that's the one that determines the shape. So sulfur has 4 electron domains, so that makes it tetrahedral. And molecular is the shape. Molecular domain. So what is that? So come over to your chart. First of all, write the ax notation here. So it's going to be, it has 4 electron domains, 3 are bonding to these oxygens, and 1 lone pair. So it's AX3E1. Okay, so come over here, find that. There it is right there. Okay, so it's in the tetra family, and it's trig pyramidal right there. Okay, it's that 3-sided pyramid because these lone pairs are pushing these bond angles down. Okay, and that's it. All right, I'll go to another piece of paper. I didn't leave enough space, so you can just do it on the back, or if you're doing online paper, you're good to go. All right, next one they want is SF4. Okay, so we've given complete octets to everybody. So we have 8, 8, 8, 8. All right, that's 32. We have to have 34 though. So that means there's going to be another lone pair. What I'm going to do is draw an arrow here, like that, back and forth, and there's another lone pair. So that means the central atom has 1, 2, 3, 4, 5 electron domains, one of them being a lone pair. Okay, and I'm just putting that goes on the sulfur. That lone pair goes on the sulfur. Okay, so the electron domain, it's got 5, so go to your chart, and there's the 5s. It's part of the trigonal bipyramidal family, and it's an AX4 because 4 of them are bonding, 1, 2, 3, 4, and 1 is lone pair, so it's an AX4E1 right there. So that forms a seesaw. Okay, so, and molecular domain again is the actual shape. This is the family, this is the actual shape based on whether it has lone pairs or bonding. That's called the molecular domain, and that's going to be a seesaw, like a teeter-totter is an old-fashioned name for a seesaw, teeter-totter. A seesaw is the old-fashioned name for a teeter-totter, okay? All right, so there is that one. All right, let's keep going. And the next one we have is D. By the way, notice this is an extended octet. They didn't ask you that, but just notice that. PF6 minus, that's definitely going to be an extended octet. Okay, so PF6, because you got 6 atoms bonded to the central atom. And it's a negative. Okay, notice this would give us an odd number, which would make life difficult. And there are occasionally some that have odd numbers. But you're going to add that negative sign. That's an extra electron. So now we have an even number is 48. So this is definitely just going to look like this. Too many. Let me get rid of that one. Okay, and they can be more evenly spaced than what I showed, like that. So here's fluorine. Okay, so there's 6. So all these have 8. So 6 times 8 is 48. That's it. That's the deal. Okay, so this has 6 electron domains. Okay, 1, 2, 3, 4, 5, 6 place where there's electron. No lone pairs because you've used up all 48, and that's 8, 8, 8, 8, 8, 8. That's 48. Everybody's good. Everybody has an octet. So 6 electron domains. So come to your chart right here. The 6s are these down here. It's the biggest one that there is. That's the octahedral family. And since there's no lone pairs, let's write the X notation for this. It's A, X. All 6 of them are bonding, and there's no lone pairs left over. So that makes AX6E0 is this one right here. It means it's the octahedral family, and it's actually an octahedral shape. That's the shape that it would have. Okay, and that's the answer to that. Okay, let's keep going. Where are we? NH3Cl plus. Okay. Okay, and that's a Cl plus. Okay, so we continue with NH3Cl plus. I had to take a quick break, so I went ahead and drew this. So nitrogen is 1 times 5 valence, 3 times 1 for hydrogen, and the chlorine is 1 times 7, but it's a cation. It has a positive charge. So that means you actually have to take away an electron, okay? It's lost an electron. So it's 5 plus 3 is 8, plus 7 is 15, and then you take away 1, so you have 14 electrons in all. Okay, so the way it would draw like this. Now, how do you know Cl isn't the central atom? Well, you know that ammonium is a central atom. Ammonia is a molecule that we're familiar with. It's ammonia. It's what you use to clean in your house. Okay, so that's an atom, and then on the other side of nitrogen, where there's usually nothing except a lone pair, there's now a chlorine. And everything works. You have full octets here, and you've used all 14 electrons. So this is the central atom is nitrogen, so it has 1, 2, 3, 4 electron domains. Let's write the notation. So let's write this. And so it's A, X, 1, 2, 3, 4. All 4 are bonding, so X is 4. The nitrogen has no lone pairs. All of them are bonding to an atom. So it's AX4E0. That's just, as we know by now, is tetrahedral. AX4E0, so it's tetra, tetra, and tetra for that. Okay, all right, let's keep going. There's one more to go, and that's N3 minus. That's an interesting one. I don't know, I've never done that one before. Let's try that. So N3 minus. Okay, so clearly that's going to have to be some sort of linear molecule, but it might be bent in some fashion. Just going to draw it like that. It's just 3 nitrogens. So okay, and nitrogen is 5. And then you're adding an E minus also. So you're not, this time you're adding 1. Up here you were subtracting 1 because it was a positive charge, negative charge. So that's going to be 16. Okay, let's go ahead and create what this gives us. And you put the octets around the outside atoms first, and then you deal with the central atom. Okay, so there you have 16 electrons, but the central atom doesn't have an octet, so this looks just like what we did with CO2. We're going to take this one and this one, and we're going to come in here and create double bonds, and that's what that would look like. All right, so we're interested in the central atom as far as electron domain and geometry, for geometry. Okay, so it has 2 bonding domains, 1, 2, that's it. And it doesn't have any lone pairs. So that's going to be an A, X, 2, E, 0. Remember, double bonds still count as 1 bonding domain. It's one location where you have electrons. All right, and that's that. So that's going to be linear, just like CO2. Okay, and that takes care of that particular problem. Let's just take the day off on that one. Okay, I won't even ask you that. That means we're done. So this is all the answers for the day 75. It's really not that long of an assignment, and get that done hopefully by Monday, and that'll do it for that. So Monday we get started on buffers, and I look forward to teaching you that, because that's a big subject on the AP. They're definitely going to ask you buffers, acid-base buffers on the AP. Okay, so have a good day, and we'll see you in class.